As promised in the last lecture, we'll start with the dissection principle. And as we discussed last time, this is essentially decomposing the dynamics of the process into independent and identically distributed blocks. So you have this x1, x2, x3, this process. We'll divide it into IID blocks. And each block will consist of a piece of path from between two consecutive visits of a fixed state. So we'll start with one state and we'll wait for the first time we'll come back to that state. That would be our first piece. Starting from that time, we'll go wait for the path to come back, Markov chain to come back to that state again. That's our second piece, and so on. Now this will be very useful. The entire process, instead of looking at it as an entire process, looking at it at these kind of IID pieces knitted together. And the idea is that once we have this IID structure, we can use that to apply laws of large numbers, central limit theorem, etc. Now this, instead of calling it dissection principle, in many books, they will also call it regeneration. But we'll stick to this phrase dissection principle. Now this idea of this is very easy, as I described it in these words. That is exactly what is going on. However, the details is notationally slightly complicated. And the proof of this result is really long. So what we will do is we'll first try to understand the theorem with the help of pictures, and then we'll go for the proof. Even to understand the notation, it will take a while. So that's why what we will do is we'll not be able to complete the proof. Of course, I could have stated it and then proved it today itself, but I want to take 2 days to do that because this is a really long proof. And moreover, I'm doing it on this medium, this online medium, which makes it even harder. So let's start from this picture. So suppose you have a Markov chain whose state space is 0, 1, 2, 3. Okay. So you can think it, any example would do. For example, a Markov chain, simple random walk on 0, 1, 2, 3 with reflecting barriers. So 0 and 3 reflects, 1 and 2 doesn't. Okay. So you can think of that. It's just one example. You can think of many other examples. Now suppose I decide, and this is quite a standard thing to do, to denote this Markov chain dynamics as follows. In this direction, I'll plot the time. So the horizontal axis will be the time axis. Vertical axis is the space axis in the sense that it tells you where the Markov chain is at that particular time. So the Markov chain says starts at 0. So at x0 is 0. So therefore, you start this at 0, 0. Then say at time 1, it goes to 1. Then I'll draw the point 1, 1. And then I'll join this 0, 0 with 1, 1. Okay, this is just a way of representing the Markov chain. Say at time 2, it comes back to 0. Then I'll also put a point at 2, 0 and then join this line. Similarly, at time 3, the Markov chain goes to 1. Then at time 4, it goes to 2. At time 5, it comes back to 1 again. And time 6, it goes to 0. So this is the representation. This is the graphical representation of a Markov chain. So in this case, just think of it as a simple random walk with reflecting barriers. Okay? So once it comes back at 0, next step has to be 1. Anyway, it doesn't matter. Any Markov chain will do as long as you understand that this is how it is represented. So this is the time axis, this is the position axis or the space axis, and then you represent it using this diagram. Now from this diagram, it should be clear that you started at 0, then you came back to 0. So this is what we will call, sorry, I went to the wrong page. This is what we'll call the first excursion. So the Markov chain starts at 0 and then comes back to its starting point. So this is what we'll call the first excursion. Similarly, this would be the second excursion. You go and then come back. Now what we will show, and then you can also have a third excursion, fourth excursion, and so on. What we will show is that these excursions are going to be IID in some sense. Okay? So in particular, the first excursion is going to be independent of the second excursion. And the second excursion would be independent of the third excursion, and so on. In some sense, you should think of it as a manifestation of Markov property, because whatever happens here may depend on this one only. So this is the future. Think of the second excursion. Think of the Markov chain from here all the way here. Now this is basically, this part is the future, this is the present, and this is the past. So therefore, we know that the future, given that the past and present, should not depend on the past. So in other words, these positions should not depend on these positions here. The only dependence should come through this present, which is common between the two excursions, this point here. But the point is here, the Markov chain, by definition, it has come back to 0. So we know that the Markov chain at that point is at 0. So there is nothing random about it, it's 0. So therefore, the only common point which could have been the potential dependence between these two parts is actually deterministic in this case. Okay, and therefore we should expect that these two parts are independent. Of course, this is just the intuition, it's not formal. The major problem is that where it comes back is random. You don't know exactly when it comes back. It may so happen that the first excursion would look like the second one. Okay, so it would have gone up to 2 and then came back. Or it could have stayed in between 1 and 2 for some time and came back. Okay, there are various things that could have happened. So the prime problem is, where the first excursion will come back. So what is the first return time of the Markov chain is random. And that is where the challenge lies. Okay, in order to formalize this excursion being IID, the challenge lies in the fact that the return times, by the way, this will be the return times. This is the first return time to 0. This is the second return time to 0 and so on. These are random. And that's where the challenge lies.